What if we could drill a hole straight through the Earth, from one side to the other? As we pass into the Earth's crust, solid rock surrounds us, and the weight of the planet begins to press down.
Deeper into the crust, rocks become heavier and hotter, and the pressure begins to rise dramatically. In the upper mantle, solid rock begins to flow under immense heat and pressure, like a slow-moving, glowing river.
In the lower mantle, pressure and gravity reach staggering levels, bending rock almost like it's a liquid. The outer core is a flowing ocean of molten metal, where gravity begins to weaken and the planet's magnetic dynamo stirs.
Near the inner core, heat and pressure reach unimaginable extremes, and gravity weakens towards zero at the planet's center. At the very center of the Earth, solid metal endures unimaginable heat and pressure, while gravity virtually disappears. As we rise toward the outer core, the solid inner metal gives way to a molten ocean. Rising through the lower mantle, the molten metal solidifies into dense rock, and pressure slowly eases while gravity returns.
As we near the upper mantle, rocks cool and harden, and gravity returns, guiding us back toward the crust. Approaching the crust again, the rocks cool and solidify, and gravity returns fully as we near the surface.
Emerging on the opposite side, gravity stabilizes, and the surface welcomes us back from an extraordinary journey through Earth.
During a fall through Earth, gravity decreases toward the center, creating a unique free-fall oscillation before pulling us back toward the opposite surface. Temperatures rise from the cool crust to the molten outer core, reaching thousands of degrees at the inner core, far hotter than any furnace on the surface.
Pressure increases dramatically as we descend, compressing rock and metal, shaping the behavior of Earth's interior materials.
Gravity weakens as we near the Earth's center, allowing particles to float, before gradually pulling everything back toward the opposite surface. Convection currents in the mantle and outer core drive molten and semi-solid rock, transporting heat and shaping Earth's magnetic field. Earth's rotation twists the molten outer core, creating convection spirals and generating the planet's magnetic field. Heat from deep within the Earth rises upward, driving tectonic plates, fueling volcanoes, and reshaping the planet's surface.
Sound becomes seismic here, racing through solid rock, slowing in molten layers and revealing Earth's hidden interior through vibration.
Across the planet, seismic sensors would detect these vibrations instantly, revealing the Earth's layered structure in precise detail. Under extreme pressure, the rock walls would fracture and flow inward, causing the hole to collapse almost immediately. As the hole collapses, molten rock and metal surge inward, sealing it shut under immense heat and pressure. The collapsing hole would trigger powerful earthquakes, sending shock waves through the crust and deforming the surface above.
The disturbance would even reach the atmosphere, sending pressure waves through clouds and subtly disrupting weather patterns.
Over time, Earth would absorb the damage, sealing fractures and restoring balance through its immense geological processes.
Even with advanced technology, heat, pressure, and lack of oxygen would make survival impossible within minutes.
No known material could survive the crushing pressures and scorching temperatures within Earth's mantle and core. As objects descend, increasing heat gradually melts their surfaces, demonstrating the extreme temperatures inside Earth. Extreme pressure deep inside Earth compresses and crushes objects, combining with heat to destroy structural integrity long before reaching the core. The intrusion of a void disturbs molten layers, creating swirling currents and ripples in Earth's natural convection flows. Disruption in the molten outer core would distort Earth's magnetic field, twisting lines of flux and affecting geomagnetic stability.
Over time, heat redistributes within the core, restoring convection patterns and thermal equilibrium after the disruption.
Over weeks and months, surface cracks close, debris settles, and the land gradually returns to a stable state. Over time, ocean waves lose energy, currents normalize, and sediments settle, restoring the sea to equilibrium. Atmospheric pressure waves gradually dissipate, clouds smooth out, and wind patterns return to their normal, stable flow.
Over time, the outer core's convection stabilizes, restoring Earth's magnetic field and its protective geomagnetic balance.
Over centuries, fractures solidify, tectonic plates settle, and landscapes stabilize.
Sediments resettle, currents stabilize, and marine ecosystems gradually return to balance after the seismic disruption.
Clouds and wind gradually return to normal, restoring the atmosphere's natural balance and predictable weather patterns.
The outer core's convection restores fully, realigning the magnetic field and stabilizing Earth's geomagnetic poles.
Mantle convection gradually stabilizes, redistributing heat evenly and restoring steady internal flow.
Over centuries, tectonic plates slowly adjust, releasing stress and forming mountains, while valleys and fault lines stabilize. Over time, vegetation and wildlife gradually return, restoring ecosystems and the natural balance of the land. Ocean surfaces calm, currents stabilize, and marine life gradually thrives, restoring the balance of aquatic ecosystems. The outer core's convection fully stabilizes, aligning magnetic poles and ensuring a uniform geomagnetic flux. Over time, heat distributes evenly from the core to the crust, establishing long-term thermal equilibrium within Earth.
Over time, ocean currents normalize, distributing heat and nutrients evenly, and restoring a stable global circulation system.
Forests, rivers, and wildlife flourish in harmony, reflecting the full recovery and balance of Earth's ecosystems. Heat, magnetic fields, oceans, and atmosphere are fully synchronized, maintaining a stable global energy balance. Day-night cycles, seasons, and Earth's orbit remain stable, demonstrating the planet's long-term resilience. From core to crust, oceans to atmosphere, and wildlife to magnetic fields, all Earth stands fully recovered, with all systems in harmony, demonstrating the resilience and balance of our planet.